The rope, nobody takes it seriously. A thin strand dropping from the clouds, pale, almost transparent, swaying like it can't quite make up its mind. The kind of thing you glance at and move on from because nothing that looks like that could actually hurt you. That assumption has ended badly for a lot of people. A rope tornado? It looks like nothing. It looks like a wisp. The kind of thing you might see and think, is that actually a tornado? It is, and it can kill you. Rope tornadoes are the most frequently observed tornado shape on Earth. They're thin, sinuous, winding funnels that twist across the landscape like a ribbon cut loose from the clouds. Some look like a single strand of smoke. Others coil and spiral in slow, hypnotic curves before snapping back the other direction. Here's what most people get wrong. When a tornado looks like a rope, it's usually dying. That graceful shape is called the rope-out stage. The storm's rotation is weakening. The funnel is being stretched thinner and thinner as energy drains from the system. A rope tornado is often a tornado in its final minutes, wringing itself out before it dissolves. But the final minutes are a lot of work in that sentence. A rope tornado can still carry winds over 100 miles per hour. It's narrow, sometimes only a few yards wide at the contact point, but that concentrated energy is deceptive. The damage path is narrow, but inside that path, everything gets torn apart. Fences stripped, vehicles flipped. A rope tornado crossing a road leaves a scar in the pavement that looks like something deliberate, like a scar made with intent. They're also nearly impossible to track. Their erratic, dancing movement makes predicting their path close to futile. A thick wedge moves in a predictable line. A rope tornado dances. You watch it move northeast, you plan accordingly, and then it pivots 50 degrees and goes somewhere else entirely. By the time you've processed the change, it's already there. And then there's the one that doesn't die. There are documented cases where a tornado fully ropes out, appears to lift from the ground, and then drops back down seconds later with renewed intensity. The storm above it never stopped rotating. What looked like a goodbye was just a pause. Rope tornadoes are also some of the hardest funnels to see. Because they're so narrow and often wrapped in precipitation, the visible condensation funnel can be nearly transparent. The tornado is there. The rotation is happening. You just can't see it until the debris cloud at the ground gives it away. This is level 0, the weakest shape, the thinnest funnel, and it can still take a house apart. What does a tornado look like when it stops roping out and starts growing up? What happens when something this deceptive gets organized? The cone. A rope tornado is a storm in decline. A cone tornado is a storm that has found its footing, wider at the top where it connects to the rotating wall cloud, tapering cleanly toward the ground in a recognizable geometric shape. The cone is what your brain builds when someone says the word tornado and actually means it. It's the image on every weather warning graphic, the shape children draw, the funnel that turned storm chasing into a profession, and that familiarity is exactly what makes it dangerous. A cone tornado signals a storm in its mature phase. The supercell thunderstorm producing it has organized its rotation into something coherent and sustained. The low-level wind shear is cooperating. The updraft is strong and stable. Everything about the storm's architecture is working together, and the result is this cone. Clean, purposeful, evidence that the tornado has settled into a rhythm. Cone tornadoes typically carry winds from 86 to 135 miles per hour at EF1 to EF2 ratings. Shape suggests organization. Damage determines the rating. They're wide enough to be unambiguous from a distance, but narrow enough that their damage path is still relatively contained, a few hundred yards across, enough to level a neighborhood block while leaving the next one standing. The width is telling you something. A cone that's narrowing is a storm weakening back toward that rope stage. A cone that's widening, growing broader at the base as you watch, is a storm intensifying. It's pulling in more air, more energy, more rotation. It's becoming something worse. Here's the trap that cone tornadoes set specifically because of how recognizable they are. People think they understand them. They see the cone, they recognize it, they believe they can judge the distance and calculate their escape window. They think familiarity equals safety. Judging a tornado's distance by sight alone is notoriously unreliable. The atmosphere distorts visual perception. Rain curtains around the funnel obscure the base. A cone that appears 3 miles away could be 1 mile away, moving at 40 miles per hour. You have roughly 90 seconds. The math does not favor you. The cone is also the last shape where a tornado still looks like what people expect. After this, the shapes start breaking the rules. They stop being recognizable. And that is when the real danger begins, because when a cone stops tapering and starts bending, when the funnel no longer falls straight, you're no longer looking at a cone. You're looking at something that lies to you about where it actually is, the elephant trunk. Some tornadoes fall straight down from the clouds. Clean, vertical, predictable. Some of them curve. An elephant trunk tornado descends from the storm base and then arcs outward at an angle, curving or sweeping toward the ground in a long, sinuous bend that genuinely resembles an elephant's trunk reaching down. The funnel bends forward, sideways, or sweeps in a curving arc that tracks a different direction than the storm cloud moving above it. The curve happens because the atmosphere is pulling the tornado in two directions simultaneously. The storm moves one way, the surface winds blow at a slightly different angle. The funnel, caught between those competing forces, bends to accommodate both. The atmosphere is literally sculpting the tornado's shape in real time, reshaping it mid-descent like wet clay on a spinning wheel. Elephant trunk tornadoes are typically associated with EF1 to EF3 intensity, with winds ranging from 86 to 165 miles per hour. But that range is wide for a specific reason. The shape doesn't tell you the wind speed. A gently curving trunk and a violently curving trunk can both carry devastating winds at the contact point. The elegance of the shape is not a measure of its restraint. This is where elephant trunk tornadoes become genuinely treacherous beyond their wind speed. The visible funnel is displaced from the actual ground contact point. The condensation funnel you're watching curves in one direction, but the actual destruction, the rotation tearing through the surface, is happening somewhere different from where the funnel appears to be. If you're navigating based on the visible funnel position, you're looking at the wrong location. Storm chasers and emergency managers know this. Civilians making split-second decisions about which direction to drive often don't. In the southeastern United States, where tornadoes frequently occur in high-humidity environments with low visibility, sometimes at night, elephant trunk tornadoes wrapped in rain become invisible. No dramatic silhouette against a green sky, no funnel to see, just a rotation signature on Doppler radar and a debris field that wasn't there 10 minutes ago. The atmosphere can make a tornado that looks otherworldly when visible. It can also make one that cannot be seen at all until the damage is already done. An elephant trunk is a tornado that lies. And EF2 damage, roofs torn from homes, trees snapped mid-trunk, vehicles thrown, is the price of believing it. But the elephant trunk at least gives you something to track. Something with visible edges, something with a shape. The next level doesn't give you edges, it gives you geometry so precise, so symmetrical, that it stops looking like weather and starts looking like engineering. And that's the most terrifying thing about it. The stovepipe. A stovepipe tornado is a geometric statement, perfectly cylindrical, uniform in width from the cloud base to the ground, no taper, no curve, just a clean, straight tube of rotating air as if someone installed a pipe between the storm cloud and the earth and opened it all the way. It looks artificial, too precise to be natural, too symmetrical to have come from a weather system and not an engineering diagram. The stovepipe shape appears when a tornado reaches equilibrium. The inflow at the surface matches the rotation aloft. The storm is feeding itself at a perfectly sustained rate. Nothing is accelerating dramatically, nothing is weakening. It has found a terrible kind of balance, and that balance corresponds to peak intensity. Stovepipe tornadoes are frequently rated EF3, with winds from 136 to 165 miles per hour. They appear at the mature to violent stage of a tornado life cycle, after the cone has organized fully and before the system either intensifies into a broader structure or begins to weaken. The stovepipe is the tornado at work. Clean, organized, ruthlessly efficient at converting atmospheric energy into destruction. This shape produced some of the most iconic imagery from the 2011 super outbreak, the largest tornado outbreak in recorded history, with 355 tornadoes touching down across the United States over 4 days in April. Multiple stovepipe tornadoes were documented during that event, photographed against the flat plains of Alabama and Mississippi, in frames that circled the globe within hours. The Tuscaloosa-Birmingham tornado, rated EF4 with winds up to 190 miles per hour, displayed stovepipe characteristics during portions of its life cycle. It was on the ground for 80 miles. It killed 64 people. The photographs from that storm look like something between a science diagram and a nightmare, a perfect gray cylinder consuming a city. The stovepipe also reveals something important about how tornadoes are perceived. Width gives you information. A stovepipe 200 yards wide is dangerous. One that's 600 yards wide is catastrophic. Unlike what comes after it, the stovepipe shows you its edges honestly. You can see where it ends. You can measure it, at least approximately. That clarity is almost a mercy, because when the bottom of a stovepipe starts widening, when the cylinder becomes a column and the column becomes a wall, when you can no longer see where the tornado ends and the sky begins, that's when you're no longer looking at a stovepipe. And that's when a single funnel stops being enough. Because sometimes the storm doesn't settle for one rotation. Sometimes it divides. The multi-vortex. Up to this point, every shape has been a single funnel. One rotation, one contact point, one thing to track. The multi-vortex tornado breaks that rule. When a large, powerful tornado's main circulation becomes sufficiently organized, it generates multiple smaller vortices, called suction vortices, spinning rapidly around the interior of the parent funnel. These subvortices orbit the central core like electrons around a nucleus, sometimes visible as brief, bright flashes within the larger dark mass of the funnel. They are not weaker than the parent tornado. They are often more intense at the contact point. Suction vortices contain extremely concentrated rotation, producing localized wind speeds that can exceed the measured average of the parent storm. They're responsible for the seemingly random damage patterns left behind by large tornadoes. Why one house is leveled to the foundation, while the house 40 feet away has its shutters intact. The suction vortex passed over one and missed the other. Not random, just terrifyingly precise. Multi-vortex behavior represents a tornado that has accumulated so much rotational energy that a single vortex can no longer contain it. The system fractalizes. The tornado becomes more than the sum of its parts. The tri-state tornado of 1925, the deadliest tornado in American history, with 695 confirmed deaths across Missouri, Illinois, and Indiana, is believed by researchers to have involved multi-vortex behavior. It may explain the unusual width of its damage path and the extreme lethality that seemed disproportionate even to its size and duration. It was on the ground for 19 miles. No photographs exist of it at peak intensity. We rated it retroactively from the wreckage it left behind. At this level, the tornado has stopped being a single thing. It has become a system. But what happens when that system spawns something outside itself entirely? What happens when the storm produces a second tornado, separate, independent, orbiting the first like a moon around a planet? The satellite. A satellite tornado is not a suction vortex. It is not contained inside the parent funnel. It is the second tornado. It forms outside the main circulation entirely and begins orbiting the primary storm at a distance of several hundred yards to over a mile. Its own contact point, its own damage path, running parallel to the larger tornado, chasing the same track, and almost never seen in time. Satellite tornadoes are rare. They require a parent storm of exceptional organization and intensity. The mesocyclone, the large rotating column within the thunderstorm, must be powerful enough to sustain two simultaneous circulation centers. It's a storm operating at near maximum atmospheric efficiency. The danger is not the satellite tornado's wind speed. The danger is where your eyes are. Your eyes are on the main funnel. Your brain is tracking the large storm. You've calculated its direction. You think you understand what's coming. You don't see the satellite until it's already close, because your attention never left the primary. And now there are two tornadoes, moving in slightly different directions, at the same time. At this level, the tornado has become a system with satellites, not a funnel, a weather event with its own orbital mechanics. And yet this is still not the top. There is one shape above this, one shape that meteorologists describe quietly, carefully, the way you describe something you hope you never see again. The shape that represents the atmospheric ceiling of measured tornado destruction. But here's the thing about ceilings. The atmosphere never agreed to one. The wedge. There are moments in the storm chasing when the radio goes silent. Not static, not interference. Everyone in the vehicle has simply stopped breathing. A wedge tornado does that. A wedge tornado is defined by one measurement. It is at least as wide as it is tall. The funnel is so massive at its base that it appears to have no funnel at all. It's a wall, a rotating wall of darkness stretching from the ground to the cloud base, edge to edge across the horizon, as wide as a city. Some wedge tornadoes are half a mile wide. Some are a mile wide. The widest ever recorded. The El Reno tornado of May 31st, 2013. 2.6 miles across at peak width. 2.5 miles, the length of roughly 45 football fields placed side by side. Spinning at 296 miles per hour. Moving erratically, changing direction multiple times, behaving in ways that defied standard storm motion models. It killed storm chasers. Experienced professional storm chasers. Tim Samaras, his son Paul, and colleague Carl Young, with decades of combined field experience, with radar in their vehicles, with every tool modern meteorology provides. They were caught by a circulation that extended far beyond the visible condensation funnel. The tornado was bigger than what they could see. The 1999 Bridge Creek Moore tornado, recorded at 302 miles per hour by Doppler radar, the highest wind speed ever measured near the surface of the Earth, displayed wedge characteristics at peak intensity. It was on the ground for 85 minutes. It killed 36 people and injured 583. The damage path stretched 38 miles. Wedge tornadoes are almost always violent. Not all wedges reach EF5, but when the shape appears, it signals a storm with the structural organization and energy accumulation to produce catastrophic, irreversible damage. Entire subdivisions removed, foundations scoured clean, trees debarked by flying debris. Inside the wedge, multi-vortex behavior is happening simultaneously. Subvortices orbiting within a 2-mile wide circulation, each carrying localized wind speeds potentially above 300 miles per hour. The damage is not uniform. It's chaotic within the chaos. Completely obliterated structures standing next to structures with moderate damage, determined entirely by whether a suction vortex passed directly overhead or 100 yards to the left. At this scale, the tornado stops being a weather event in any ordinary sense of the phrase. It becomes a geography, a temporary feature of the landscape as real and as present as a ridge or a river. People in the path of a wedge tornado have described not hearing it approaching, but feeling it as a pressure change so abrupt and complete that it registered as physical impact before any sound arrived. The atmosphere inside a wedge circulation is doing things that have no peacetime equivalent. Debris lofted to altitudes above 60,000 feet. Vehicles carried miles from their origin. Signatures on Doppler radar are so large that meteorologists have initially misidentified them as ground clutter because nothing that size should be rotating that fast.